Hey guys, so today we're going to be starting Unit 3, and Unit 3 is actually made up of 4 different chapters, but each one is fairly tiny. Each one is only about 3 lessons. So instead of doing a quiz after every single chapter like we normally do, we're going to do quizzes after every other chapter. So we'll do 2 chapters and then a quiz on those 2, 2 more, a quiz on those 2, and then your unit test will be on all 4. So the first chapter that we're going to be going into is circle geometry. Okay, so just so you know, the chapters we're going to be covering in this unit are chapters 9, 3, 4, and 8 in that order, which I know is all over the place, but that's what we're going to be doing. Chapter 9 is circle geometry, and today's lesson is central and inscribed angles. So just a couple definitions that you'll need to know for circle geometry that you should already be familiar with. Diameter is the distance across the middle of a circle. So if we have a circle, that would be the diameter. The radius is the distance from the center of the circle to anywhere on its edge, and that is going to be half of the diameter. And then the circumference is the distance around the entire outside of the circle. That is equal to pi times the diameter. And now for a couple definitions that you're probably not familiar with. A chord is a straight line that connects any 2 points on the edge of a circle. So a chord could look like this, or like this, or whatever. Technically, the diameter is also a chord since it connects 2 points on the edges. But any straight line that goes essentially the whole way across a circle, anywhere in the circle, is a chord. And then an arc is if you have a circle, any part of the outside of that circle or the circumference of a circle is an arc. So this could be an arc, or this whole thing could be an arc, that sort of thing. And then a tangent is when you have a circle, you have a straight line outside of that circle that just touches the circle's edge at one point. So this would be a tangent. Okay, so let's get into the actual angles stuff of this lesson. So there are 2 main types of angles in circle geometry. We have the central angle and the inscribed angle. The central angle is going to have the vertex, which is the point of the angle, in the center of the circle, and then each arm that's coming off of that angle is going to be a radius. So what that would look like is, if this is the center of our circle, the central angle would have the point of the angle, so the vertex in the center, and then each of these arms goes from the center to the edge of the circle. So each of those arms is a radius. So that is what a central angle would look like. And by the way, this side could also be a central angle as well. And then an inscribed angle is going to have its vertices on the edge of the circle. And each arm is then a chord because it goes from one point to another on the edge of the circle. So that is what an inscribed angle would look like. Of course, possibly facing any way inside that circle. The important part to note is that when you have 2, like a central and an inscribed angle, there are some calculations that you can do with them as long as they share the same endpoints. So when I say shared endpoints, what I mean is that the arms end in the same place on the edge of the circle. So if we have 2 inscribed angles that have shared endpoints, they are going to have the same degree for their angle. So in this circle, I've drawn in 1 inscribed angle already. I can put in another one, and it's going to have the same endpoints, but a different vertice. So like that, for instance. Again, both of them have arms that end at the same place, but they have different places where they hit the edge of the circle. So I've got one inscribed angle right there and another inscribed angle right here. Both of those would have the same measurement. So if I told you that this angle here is 20 degrees, you would be able to tell me that this angle is also 20 degrees because we have two inscribed angles with the same endpoints. They must be the same magnitude. You can also compare a central and an inscribed angle as long as they have the same endpoints. So a central angle will always have an angle that is twice the size of the inscribed angle. Another way of saying that is that the inscribed angle will be half the size of the central angle. So you might remember that as that the central is 2 times the inscribed angle, or the inscribed is the central angle divided by 2. Just so you know, these are not formulas that you will get, so you do have to memorize this kind of rule. So if I have this central angle here, the inscribed angle would have to have the same endpoints, but its vertices would need to be on the edge of the circle somewhere. So I would have this inscribed angle there and the central angle right here. Now, if I told you that this central angle was 88 degrees, you would be able to tell me that the inscribed angle must be 44 degrees because the central angle will always be twice as big as the inscribed angle. You could also, of course, go the other way. So say I told you that this was a 15-degree inscribed angle, you could just double that to figure out that the central angle is 30 degrees. Another kind of rule to know has to do with something we call the central angle triangle. So essentially this means if you take a central angle and then connect the ends of the 2 arms with a chord, you will form an isosceles triangle. And in an isosceles triangle, 2 of the angles are always equal to one another. In this case, it'll be the 2 non-central angles that are equal to one another. And in order to solve these problems involving triangles, just remember when you have a triangle, the 3 angles will always add to 180 degrees. So for example, if I had my circle, and I'm just going to draw in a central angle. So this is my central angle here. I can connect these 2 ends of the arms with a straight line, and that straight line is the chord. So this is my central angle, this is my chord. When I do that, I make this isosceles triangle, and these 2 angles down here, so not the central angle, the other 2 angles, will be equal to one another. So if I told you that my central angle here was 80 degrees, and I wanted you to tell me what the other 2 angles are, the way we would do that is we would say, okay, I know that the entire triangle, 3 angles, add to 180. So if I just do 180 minus the angle that I know, that's going to give me, in this case, 100 degrees. I now know that that 100 degrees accounts for the remaining 2 angles. And because I know that those remaining 2 angles are identical, I can just take the 100 degrees and divide it by 2 to split it between those 2 angles. And I then get that each of those angles must be 50 degrees. Another type of kind of special triangle with inside of a circle is called an inscribed angle semicircle. This is a triangle that's used that's made using an inscribed angle and the diameter of the circle. This only works if the endpoints of the arms happen to fall on a semicircle, meaning that they fall halfway around the circle. If that's the case, though, your inscribed angle will definitely be 90 degrees. So what that would look like is, say that is the center of the circle. If I have an inscribed angle that looks like this, and I can connect those two endpoints by going through the center, like so. Now I've connected the two endpoints with a chord that happens to be the diameter. That means that my inscribed angle is definitely 90 degrees. Another way that you can compare angles is if you have opposite central angles, which are two central angles that form a circle. And just a reminder, a circle is always 360 degrees. So for instance, if I had a central angle that looked like this, the opposite of this central angle would be this central angle, the one that is essentially the obtuse version of the acute one that I drew initially. And as you can see, they form a circle in the center here. So if I told you that this central angle right here is 70 degrees, in order to find out what its opposite central angle would be, I would just take 360 degrees, the degrees in a circle, subtract the central angle that I know, and oh my gosh, is that 290? 360 minus 70 is 290. So that would be the opposite central angle. The last thing that we're going to look at here is quadrilateral opposite angles inside of circles, and we can do this for both inscribed angles and when comparing central and inscribed angles. The one thing that's important to note whenever you're comparing angles is that it only works whether you're comparing inscribed angles with inscribed angles or central angles with inscribed angles. It only works if they share endpoints and they're facing the same direction. So for example, all the ones that we've already looked at, the central angle and the inscribed angle are facing the same way as each other. They both like bump out in the same direction. And that was also true for the inscribed angle ones that we looked at. So we had like two different inscribed angles, these had to share endpoints, but they were still facing the same direction as each other. When we're talking about quadrilateral opposite angles, they're no longer facing the same direction, they're facing towards one another, and so we have to use different rules. So if we have opposite inscribed angles, they're not going to be the same as each other, the way they would be if they were facing the same direction. Instead, they're going to add to 180. They do still need to have the same endpoints, though. That hasn't changed. So for instance, if I had one inscribed angle that looked like that, again, its angle is on the edge of the circle. That's what makes it an inscribed angle. And my second inscribed angle has the same endpoints, but instead of facing the same direction as it, it is facing the opposite direction. So these two like bumps are coming towards each other. That means that they add to 180 degrees. So if I told you that this angle was 100 degrees, you could tell me that the opposite inscribed angle was 80 degrees. So we can also use this quadrilateral rule when comparing opposite central and inscribed angles. In order to do that, we're actually going to apply our opposite central angle rule, where the two central angles add to 360, and then just compare the central and inscribed angles that are actually facing the same way. So let's go through an example of how to do that. Okay, so far I have drawn in a central angle. I'm also going to put an inscribed angle with the same endpoint still. But this time my inscribed angle is facing towards my central angle. So it forms this four-sided shape. That's why these are called quadrilateral rules, by the way, because they form four-sided shapes. So let's say I have told you that this inscribed angle here is 94 degrees. If these were facing the same way, I would be able to tell you what the other central angle is. But I can't do that directly because these are facing one another. Instead, what I'm going to do is say, okay, if this is 94 degrees, the central angle that is facing the same way as this would be twice 94. And if I look at my central angle, the one I've drawn in isn't facing the same direction as this 94, but its opposite angle is. This central angle is facing the same way as my 94. So in order to find this angle here, which I'm going to call angle A, I have to take my 94 and times it by 2, because this central angle that's facing the same way will be twice as big as the inscribed angle. So that gives me 188. Now I can apply the opposite central angle rules because they form a circle. So if I call this one that I'm looking for angle B, in order to do that, I just do 360 degrees minus the 188. That is the other half of that circle, or other part of that circle. And I get 172. So angle B would be 172 degrees. Okay, let's try a second example here, where once again I am going to have a central angle and an opposite inscribed angle. This time I want to find the inscribed angle, and I'm going to tell you that the central angle is 110 degrees. Now, once again, I cannot just divide this in half to find my inscribed angle because they're not facing the same way. But what I can do is find the opposite central angle, which we'll call angle A. So in this case, I'm going to do 360 minus the 110, which is obviously 250. And now that central angle is facing the same way as this inscribed angle. So my second step is just going to take the central angle and divide it by 2 in order to get my 250 degree inscribed angle. So depending on which angle you're given, whether it's the central or inscribed angle, you might be doing the circle rule first or second, and then either multiplying or dividing by 2, either first or second. But those are the two different processes that you can use to compare central and inscribed angles that are facing one another in a quadrilateral like that. Okay, last question, and then we're done for the day. I'm just giving you an example here that kind of puts all of this together. So I've given you 4 different angles here. I've got a central angle, an inscribed angle that is facing it, and then 2 inscribed angles that are facing the same direction as that inscribed angle, or sorry, the central angle. So if I give you any one of these, you should be able to tell me what all the rest of them are. So let's see how you do with that. I'm going to start by telling you that angle C is 40 degrees. And so pause now, see if you can try to figure this out on your own. Right away, I think the easiest thing to figure out is angle D. Because angle D and angle C are inscribed angles that are facing the same way, they are the same value as one another. So angle D is also going to be 40 degrees. I can also then find angle A. Because angle C is facing the same direction as angle A, that means that angle A is just going to be twice as big as angle C. So that is going to be 80 degrees in there. And then there's a couple different ways that we could find angle B. You could do what we were just doing in the previous two questions and find whatever the other side of angle A is and then divide that by 2. Or you could remember the rule that opposite inscribed angles add to 180. So just to kind of review this, to find angle A, I did 40 times 2 is 80. Those two are the same. And then to find angle B, you could say 360 minus 80 is 280, which would be this angle right here. And then do 280 divided by 2, which is 140. Or you could just remember the rule that 180 minus the opposite inscribed angle of 40 would also give you that. Obviously, the second way of doing it is faster, but a lot of people forget that rule or they think it's 360. This one is like kind of more intuitive, the first one here, because people generally know that a circle is 360, and then you have to memorize the rules of comparing central and inscribed angles that face the same direction anyway. So that's why I kind of like this first method more. It's the method that I tend to use, just so I don't have to memorize something extra. Anyway, that's it for today. I'll see you guys tomorrow.